All right, Chapter 7, securing the control plane. You guys remember the 3 planes of existence that we discussed that were in a device? Data plane or data plane? More officially, data plane. Data plane, I suppose. You want to call it that. Control plane, what else? Management plane, right. Out of those 3, the most important one is the control plane. Because the control plane is where all the good stuff happens. That's where your routing occurs. That's where all of the intelligent processing of data occurs. That's where your caches get built from. So if the control plane's not functioning on a device, then nothing is going to function on the device. So one of the things that you should do as a best practice standard is protect the control plane using something called control plane policing. Okay? Hardware and software that supports routing and management is the control plane. RFC 6192 discusses the need to protect the control plane from undesired or malicious traffic. Most of the time it has to do with denial of service, right? The control plane being overwhelmed with a bunch of traffic so that it can no longer process legitimate traffic, and then the CPU spikes or whatever and the device can't function anymore. All right, the primary objective is to protect that CPU and the integrity of IP routing. So I don't want to suggest that this is only a feature of a router. Switches actually have a control plane function as well, but if a switch is operating at layer 2, it's primarily doing everything at the data plane. Very little control plane functionality exists in a layer 2 switch. Multi-layer switches, that's a different scenario because we do have routing functions built in. So you can see the control plane, the management plane, the data plane. The data plane is kind of that forwarding plane that allows us to take data into one interface and send it out of the other interface. Not all traffic needs to go to the control plane. You guys heard of something called Cisco Express Forwarding, which is enabled by default on Cisco. What Cisco Express Forwarding does, it's almost like fast switching. There's kind of 3 different ways you can process data through a device. You can do process switching, which everything goes up to the control plane and then it goes back down to the data plane. You can do fast switching where some of the stuff goes up to the control plane, or at least the initial packets, and then we build our caches, and then everything goes through the data plane from that point forward. Or you can use Cisco Express Forwarding where all these caches, these forwarding tables, get constructed before data even goes. And what we're trying to do is we're trying to make sure that we always keep our data on that plane. But Eigrp, OSPF, BGP, ISIS, routing protocols, filtering traffic through policy-based routing, advanced functions in the router itself, they're still going to have to go through the control plane. So we want to make sure that we protect this because a router is supposed to route, and a router can't route if the routing protocol doesn't work. Make sense? Routing protocol doesn't work, we can't route, means the router doesn't work. So what we're going to talk about is there's 2 different methods of protecting the control plane. There's something called control plane policing and something called control plane protection. Unfortunately, the book doesn't really go into a whole lot of detail on the configuration, but what I usually do is there's a couple of documents on Cisco's website. I'll pull those up. We'll kind of just take a cursory look at how Cisco recommends you set up this control plane protection. This is sole and separate from any other protection mechanism that you're running on the device. Access lists, any kind of filtering you're doing on the interfaces, any kind of .1x, any other security feature that you're running, you should be doing this on top of that as well. Do you guys know if you guys are doing any kind of control plane protection? Yeah. It's definitely a best practice standard. Okay? All right. So we have 2 options. We've got control plane policing and we've got control plane protection. Control plane policing is more of kind of a manual way of configuring this protection to the control plane. We use something called MQC, which stands for Modular QoS for CLI. And within modular QoS for CLI, we have three functions: class map, policy map, and service policy. By the way, MQC is also used for QoS, obviously, because that's what it stands for, modular QoS for CLI. You might also see it referred to as MPF, Modular Policy Framework. In an ASA, it used to be referred to as C3PL, the Cisco Common Classification Programming Language. But all of them are the same: class maps, policy maps, and service policy. A class map is where you take data and you put it into a class. Whether it's HTTP traffic, whether it's SSH traffic, whether it's routing traffic, whatever it might be, we take that traffic and we classify it into a particular class. Policy map is what you're going to do to that traffic. Am I going to police it? Am I going to shape it? Am I going to mark it? Am I going to remark it? Am I going to rate limit it? Well, policing and shaping is kind of that concept. So policy is what you're actually doing to the traffic, and then service policy is where you're doing it. Service policy is where you're doing it. What do I mean by that? Am I going to apply this policy to an interface, like a physical interface? Am I going to apply this policy to the control plane interface? That kind of thing. Okay? So we will look at, after the break, we'll take a look at the COPP document on Cisco.com, just to give you an idea of what they recommend with regard to how you distinguish different types of traffic. Remember, we're really trying to protect the control plane, and there's only certain types of traffic that actually go to the control plane. Routed traffic, like FTP traffic and streaming video, streaming audio, that's not going to go to the control plane. Well, it shouldn't go to the control plane, but certainly Eigrp traffic, OSPF traffic, ARP, stuff like that. The other option you have is control plane protection. Very similar to COPP, but with control plane protection, you get much more granularity in what you can perform or what actions you can take against the traffic that's going to the control plane, and you don't have to use MQC to configure it, because it actually has sub-interfaces that already exist, and those different sub-interfaces provide a way to classify traffic going to the control plane, so we can apply different policies to that traffic going to the control plane. So what we're going to do is we'll take our break now, and then after the break, 15 minutes, we'll go into the actual configuration. We'll look at some of that, because they don't really get into it too much beyond what we just saw here. So I want to make sure you guys get that information. So let me go ahead and pull up the site for control plane policing. Not control plane protection, but control plane policing. Just to give you guys an idea, I'll try to zoom in too so it's a little bit easier to read up on that tiny screen. But there are several documents on Cisco's website that talk about how to implement control plane policing. And then you guys will be able to identify whether or not you're using a control plane policing function, or if you're using a control plane protection function, because we'll look at the other one as well. But there's a document here called Control Plane Policing Implementation Best Practices. All I did is go to Cisco.com and search on control plane policing. So the nice thing about this particular document is that it does talk about all the different types of platforms, the 6500 series switches, 7600 series switches, the 12,000 series routers, and all your centralized CPU-based platforms, which are like your basic ISRs and whatnot. It talks about your XR platforms, which are the they run a kind of a special iOS and a special firmware. But essentially, this document, really useful, describes the whole concept of data plane packets, control plane packets. We're not going to go through this whole thing, but I do want to hit some of the high points here. Okay, so it says here a data plane packet is essentially anything that gets forwarded from the perspective of the data plane itself, going into one interface, going out of another interface. Then you've got these control plane packets, which are used for the operation of the network itself. Routing protocols, you can see some listed here: ARP, BGP, OSPF, and so on. These are processed by the CPU or the device route processor, and that's what goes up into the control plane. Management plane, that's our telnet, SSH, SNMP, TFTP, anything that allows us to manage the file system, to manage the device remotely, and so on. So we've already seen the diagram that kind of describes the process. Cisco Express Forwarding allows data to stay on the control plane. You can see that the data flow stays on the data plane, excuse me. Data goes in an ingress interface. If it has been identified and verified by Cisco Express Forwarding, we create these caches that allow that information to stay on the data plane. Well, by the way, what is the point of keeping the data on the data plane? Speed. Get the data through the network device as quickly as possible. What we call wire speed transactions. All right? Now, management traffic, of course, is going to go up to the CPU. Control traffic is going to go up to the CPU and maybe processed down to the data plane as well. And we've got our services packets as well. So transit packets are packets that stay on the data plane, essentially. These are the ones that are going to be forwarded in hardware by the application-specific integrated services. And then we have something called receive packets. These are all our control plane and management packets that go up to the CPU for processing by the route processor. And then we have these exception IP and non-IP packets. Think about this for a second. So let's say, for example, I have a data plane packet that's going through the router, but the time to live on that data plane packet is only 1. That would be considered an exception IP packet. Because if the time to live is 1, I've got to decrement that time to live value, but because the time to live is going to get decremented to 0, now I have to send that packet up to the control plane for processing, because the router's going to have to kill that packet, and it's going to have to respond with a time to live exceeded message or some sort of message that goes back to the sender and so on. CDP packets, layer 2 keep alives, ISIS packets, these are all what we call non-IP packets, right? CDP is a layer 2 protocol, but it does allow routers to discover other routers or other devices that it's attached to. So that becomes kind of a control plane function because it's a non-IP packet. ISIS actually operates at layer 2. Even though ISIS is a routing protocol, you guys ever run ISIS? Or we don't really like to talk about that one too much, huh? Good old ISIS. Yeah. Anyway, it actually is a routing protocol, but it actually facilitates communication among the routers using layer 2. So that becomes kind of a non-IP packet flow as well. All right. Anyway, I'm not going to read this whole document. I think it would behoove you guys to kind of go through and look for this document and take a look at it. There's a lot of detail in here, but it's a great document that describes the concept of control plane policing. The reason why I really wanted to kind of scan through this, though, is to give you an idea of where we apply different filters and what kind of filters we apply to our control plane policing function. You can see that COP is implemented at the virtual interface between the data plane and the control plane. We call that the control plane interface. So it's kind of like a logical interface that allows us to pass data from the data plane up to the control plane. We might have some interface ACLs and some filters that are applied to the physical interface that allow us to do some rudimentary security, rudimentary filtering, which would either allow or disallow certain types of traffic through the device. But what control plane policing does is it allows us to either disallow or allow traffic to go up to the CPU, and if the traffic is allowed to go to the CPU, rate limit it, or otherwise limit it so that it can't overwhelm the CPU. So we use MQC for this process. Let me just scroll down. Here's the construction, modular QoS for CLI. We're going to use a class map command. We use our policy map, and then we use our service policy command. So this talks about the essential architecture that we use to define this control plane policing policy. As I mentioned before, the class map is what allows us to take traffic and put it into a class, whether it's EIGRP traffic, OSPF traffic, whatever it might be. The policy map is what we do to those traffic classes. It's the actual policy that we're affecting, that we're applying to the traffic class, and then our service policy is where we're doing it. Have you guys seen these configurations before? Class map, policy map, and service policy in your configs? All right. You probably have seen them for other reasons as well, not just for COPP, but you might have seen them for QoS or policy-based routing or other reasons as well. All right. So here's a basic concept. First thing you do is you typically set up access lists. Access lists allow us to define characteristics of traffic flows. Source IP, destination IP, source port, destination port, protocol, etc. We use extended ACLs because we are matching traffic flows, and we want to be able to match on where the traffic is coming from, where the traffic's going to, what the port numbers are, what the applications are. They give you some examples here. BGP is TCP port 179, for example. OSPF and Eigrp, they're not going to use transport layer functions. They're protocol 88 and protocol 89 respectively. So we would have to match those protocols based on their layer 3 protocol ID. The layer distribution protocol that's used by MPLS, or label distribution protocol, sorry, used by MPLS to distribute MPLS labels, TCP 646 and so on. These are just some examples. Obviously you want to be able to identify what traffic is important in your environment based on what protocols you're running and so on. All right, so we have routing traffic. This is the best practice architecture, by the way. We define routing traffic. We define management traffic. We define what we call normal traffic, kind of less essential traffic, but like normal traffic for the router to process at the control plane, things like an echo request, echo reply, stuff. If I ping an interface on a router, that's going to have to be processed up at the control plane. If the router has to respond with some sort of ICMP control message, time to live exceeded, destination unreachable, those are kind of normal traffic. Undesirable traffic would be something like a TCP reset being sent to the control plane to reset a neighbor relationship between routers. The SQL Slammer, just some examples. Fragments, a bunch of fragmented packets being sent to the control plane. And then the catch-all, which is basically everything else that didn't qualify in one of these other categories. I don't know if you guys use these same 5 different categories, but again, this is what Cisco recommends that you do if you're doing some sort of control plane policing. So what we have to do is we have to create access lists that match these characteristics so that we can then put that traffic into a class, and then we can apply a policy to that class. So this is what that's going to look like. Here's an access list for all my routing traffic. Some of it might apply to you, some of it might not apply, it just depends. So BGP traffic, here's BGP source traffic. What do they mean by router receive block? Any ideas? When you see the words router receive block, it's essentially the networks that the router is participating in. The addresses on the interfaces of the router. Because isn't that what's terminating? Isn't that what's terminating the actual BGP sessions or the Eigrp packets and so on? So when you see any kind of router receive block, they're talking about create an access list that specifically matches the destination IP for the packets that are supposed to go to the router. It could mean also that you have to have multiple lines for that particular rule, because you might not have a consecutive block of addresses on the router that allow you to define what's going to happen with that traffic. So here I'm saying, and again, I don't want to go through every single line, but this particular line I'm saying, okay, I'm going to permit TCP traffic from anybody as long as the source port is greater than 1024 to the router receive block as long as the destination port is equal to BGP. Make sense? Again, the router receive block would be any interface or any subnet on the router that would actually be terminating those sessions. So they've got one here, then they've got one, another one here. I'm going to permit TCP traffic from anybody with a source port of BGP going to the router receive block with a destination port of greater than 1024. And by the way, I want to see that this is a TCP established session, meaning that we're not doing a SYN, we're not doing a SYNAC. This is actually a part of an active data flow that already existed. So this would be kind of like the response traffic that would come to the router. So they've got other protocols here. They've got OSPF. They've got EIGRP. OSPF and EIGRP are kind of their own IP protocols. These are the multicast addresses that are used by OSPF. This is the multicast address that's used by EIGRP, and so on. PIM AutoRP would be something used for multicast. And then you notice here it says, etc., etc., etc. Well, it doesn't say that, but I just added 2 extra et ceteras. Ultimately, what you're building with ACL 120, I would use a named ACL personally, but what you're building with ACL 120 is all of the traffic that's relevant to control plane functions that you're aware of. BGP, OSPF, etc. We're not talking about CDP, we're not talking about, the ICMP traffic. I'm classifying this traffic by using an access list. So you're certainly not going to have all this, but you could have quite a few things. Depends on what critical protocols the device is running. Any questions about this access list? I mean, outside of the raw syntax, I'm not really worried about that. You get the gist of what they're trying to do here. Yes? No? Maybe? Did it get really hot in here? Maybe it's just me. Had a rather heated conversation during the break. All right. The next one is the management ACL. Of course, here we're going to be doing things like Telnet. Obviously, with Telnet, probably not going to allow that, so we don't necessarily have to have Telnet, but here's SSH, here's SNMP, here's web traffic, 443, FTP. Essentially, any protocol that is required for the management of the device. And that would be specific, again, to what you're doing on your particular platform. All we're doing is creating an access list that matches this traffic flow. The NOC block, that would be Network Operations Center blocks of addresses. Basically, who's going to be opening up these SSH sessions, who's going to be opening up these Telnet sessions, and so on. Okay? Then you got your normal ACL, which is all your typical ICMP traffic. This will be any to the router for echo, any to the router for echo reply, and then we might also have some of the opposite direction as well for the router to generate traffic to the outside. PIM is my protocol independent multicast routing protocol. IGMP, Internet Group Messaging Protocol for multicast. GRE, if I'm doing any kind of GRE encapsulation. If you decide that you want to classify GRE at the router level, you can. This is, again, what Cisco recommends. We don't put anything at the router level. That's our mission critical traffic. This is kind of our normal traffic. All right. Then we have an access list for undesirables. All right. So that would include anybody that voted for Trump. No, I'm kidding. Right. Undesirable traffic, fragments, TCP resets, stuff that we consider to be bad. This is a pretty difficult ACL to classify because really you don't want to block stuff that would hinder normal operations or limit stuff that would hinder normal operations. But so you might have to tweak it a little bit, kind of play with it and see what you see. All right. Then we got our catch-all ACL, which is everything else. Ultimately, you're probably going to miss some things. So you definitely need the catch-all ACL. All right, all TCP traffic, all UDP traffic, all IP traffic, all ICMP traffic. All right. All right. So now we've created our access list that allows us to essentially identify the traffic. The first part of MQC is to create our class maps. We use the class map command, and we can do either a match all or a match any. What is the difference between match all and match any? Any ideas? In a class map, you can have multiple match conditions. A match all would mean that every single condition would have to match in order for the traffic to go into that class. A match any would mean any one of those conditions would have to match in order for the traffic to go into that class. Make sense? In our case, it doesn't really matter because we're only matching against one condition, the access list. Give the class map a name, and then we can match all kinds of things. We can match access group, protocol, IP precedence, DSCP. There's actually much more than that, but in this particular case, I create a class map called routing, and I'm matching against the access list that match the routing traffic. So what happens is as packets flow through the router, they match that access list, they get put into this traffic class. We're kind of just taking our traffic and putting it into containers. Does that make sense? If I just did that, nothing would happen. Everything would still be processed the same way it's always processed because I have to do something to the classes. So here's our management class, here's our normal class, here's our undesirable class, and here's our match all class. All right? You could do something like, let me show you real quick. I could do, say, class map, match all, test, and I could say match protocol. So I can actually specify a protocol like, where is it? BGP. I could match Eigrp. You could match CBT. I don't know what that is. That means that you wouldn't have to create an ACL, but the problem with doing a match protocol is you're not really able to specify source and destination. It's just any protocol that has protocol ID 88 or whatever. So match protocol, so you could do Eigrp, or you could do OSPF. What I like to do is I like to do the match protocol with an access list and do a match all. That way I know for sure it's going to be that protocol. Match protocol uses something called NBAR. You guys ever heard of that? NBAR stands for Network-Based Application Recognition. Basically, the router becomes a packet sniffer. You can actually enable this on an interface. I can go into IP NBAR protocol discovery, and I just turned on packet sniffing on that interface, and I can see all the traffic that's going through that interface by doing a show IP NBAR protocol discovery. And it will start to classify all the traffic, how much bandwidth it's using, and everything. It's kind of cool. But basically, NBAR is being used in the case of class map to match traffic to a particular class. You can see it kind of locked up my router here. It initially, when it gets set up, it takes quite a lot of CPU cycles. But once it's running, it's relatively benign, if you're only running it on maybe one or two interfaces. All right?
So is that going to spit out stuff to you real time?
No, it's not doing debugs. It's just capturing information in the background about the flows. It's kind of using Cisco Express forwarding and some other mechanisms to identify the flows. It's poor man's version of NetFlow, basically. But it's so easy to implement because you just type IP NBAR protocol discovery. See if it actually finished now. Still working. All right.
Does it do something where you can drop it into a Wireshark?
No, it just builds a database that you can view on the router. Show IP NBAR protocol discovery, and it gives you a table. All right. So do show IP NBAR protocol discovery. Come on. Show IP NBAR protocol discovery. And what will happen is as this table gets built, the protocol, you'll just see all of the well-known protocols, HTTP, FTP, Telnet, there's probably, I don't know, a few hundred protocols the router can recognize. You'll just see input and output, byte counts, packet counts, bandwidth, bits per second. So it's really a quick way of seeing what kind of traffic is going in and out of an interface. And if you want to turn it off, you just go to the interface and do no IP NBAR protocol discovery. We've used this tool quite a bit. Customer says, man, our bandwidth is being sucked up. cheapest and easiest way to go find out what's using the bandwidth, protocol discovery. If you don't want to set up NetFlow and do other things, but okay. So we've got our class map, okay. The next thing is our policy map. So in this case, this is just a generic example. Let's take a look at the actual example. Here we go. So policy map, RTR COPP, router control plane policing. That's just the name of the policy map. I reference the class, and then I specify what I'm going to do to that class. So in this particular case, the undesirable traffic is actually allowed, but only to a certain rate. All right. Actually, in this case, it's not allowed at all because our conform action is to drop the traffic and our exceed action is to drop the traffic. Without getting into the whole discussion of QoS, we're doing something here called a dual rate, dual bucket policing scenario, where we have 2 buckets and we're collecting tokens over time, and then the protocol is allowed to use those tokens within a period of time. Doesn't matter, we don't have to get into all that. But in this particular case, that undesirable traffic is being dropped, okay? Our routing traffic, we're also policing our routing traffic. By the way, when you do see the word police, which is why it's called control plane policing, there's a difference between shaping and policing. What is shaping? Well, what's the let me just add, what is the difference? What is the primary difference between a policing policy and a shaping policy?
Shaping changes it, policing just has a universal effect on it.
That sounds good. I would have probably bought that if I wasn't an IT guy. That sounded very convincing.
Policing can actually block traffic.
Yes, so both of you are kind of right. Policing takes a very aggressive action, like dropping traffic. Shaping delays traffic, okay? So excess traffic gets delayed when it's shaped, means that it gets buffered. Whereas if I hit an excess flow in policing, I drop the excess. So policing is a very, very aggressive approach to QoS, whereas shaping is kind of a more soft approach to QoS. But what these data rates here that you're seeing, these are specifying things like committed information rate, peak information rate. There's a whole bunch of math that goes into calculating what these numbers should be. And I don't necessarily recommend that you use these numbers. This is the hard part about doing COPP. You have to really kind of identify how much bandwidth you need for these protocols. And that's gonna, remember, these are routing protocols, in this case, routing protocols that I'm sending up to the control plane, okay? So the conform action is to transmit. The exceed action is to transmit in this case. All right? Now that might seem silly. It's like, well, I'm not really doing anything to the traffic. That's true. But it's routing traffic. See, the thing about a policy map is you can't apply filters. I can't say, I'm going to put an access list on this policy map. It's not the way it works. So we have to use policing actions to define whether we're going to transmit or drop traffic. Management, we have bandwidth. You can kind of see here based on the numbers. If you look at those as kind of percentages, you can see that 8,000 is less than 100,000 or million, which is less than 100,000, and so on. So we're giving most of the data, most of the bandwidth to routing. We're giving a lot of bandwidth to management, maybe a little bit less bandwidth to normal traffic, and then about the same amount of bandwidth to our catch-all traffic, and then we have a default class which actually would never get hit because our default class would essentially match everything else. Our catch-all class would have matched everything else anyway. Maybe something that would go on the default class is the non-IP traffic, because we only did TCP, UDP, IP, and ICMP. But you get the idea. If you look at the numbers, it kind of makes sense. You can tell what has priority, what doesn't have priority. Why did I put the undesirable traffic at the top? Any ideas? Policy maps are processed from the top down.
If you don't want it, get rid of it sooner.
Yep, if it's unwanted, get rid of it. Don't process it through the whole policy map and then drop it at the end. And then routing needs to be processed next, then management, then normal. So now we're kind of ordering the policy based on priority. Okay? So that becomes our policy. The last step is to actually apply it to the control plane interface. That's the easiest step to understand because I'm just basically saying service policy input going into the control plane, apply the router COPP policy. Hopefully, I know I was kind of rushed. You know, again, I would highly recommend that you kind of go through this whole document and read it, but at least now you have a general understanding of the framework. So if you're looking at a COPP policy on your router, you know, you have you understand what a class map is, you understand how traffic gets matched to a class, and what the overall objective is. All right? Now, CPPR is control plane protection. That's a little bit different. All right? I don't know if Cisco actually has a document, a best practice document on CPPR. Looks like mostly I'm just seeing people having problems with it. All right? The reason why CPPR doesn't really have a design document is because there's not a whole lot you can do to customize it. You basically enable the feature and the router handles everything based on these predefined sub-interfaces. All right? This is what those sub-interfaces look like. You've got what we call the host interface. Now look at the arrows that are pointing to the host interface. SSH, tunnel, traffic terminating at the router, SNMP terminating at the router. What do you think the host sub-interface is used for? Any traffic that terminates directly on the router. So that's not the only thing. There are other things that could terminate on the router. But the host sub-interface, which by the way, all of these are interfaces that allow us to get to the control plane or bypass the control plane. The host sub-interface clearly is going to go to the control plane. Then I've got transit traffic, tunnel passing through the router or non-Ceph traffic through a non-Ceph interface. Okay, what does that mean?
It's using the router to get from point A to point B, but the router isn't to point A to point B itself.
Right, but it still has to process the data, right? And it still has to do higher level functioning, higher level processing. Traffic through the non-Ceph interface. Basically, this would mean traffic that maybe should have gone through Ceph, because anything that's Ceph compatible never hits the control plane. Remember that a diagram we saw? Ceph compatible traffic stays on the data plane. So what goes to the transit interface? Transit basically means into control plane, out of the control plane. It's the, if you imagine the diagram, the up arrow and then down and back out. That's why it's called the transit interface. It's anything that has to be processed through the control plane but isn't terminating at the control plane. So like Eigrp, OSPF, Bgp, those would be host interface functions. Actually, Bgp is kind of weird. It has a transit function as well. All right. Did you guys see any questions on the test about control plane protection or control plane policing? A few.
It's basically, the only question is that,
What is it?
what is it? QoS and traffic shape.
Yeah.
That's,
So obviously we've exceeded the extent of knowledge we need to know for the test, but all right. And then the last one is the Ceph exception interface. So this is, I actually said this for the last one. This is probably more appropriate for this one. This is traffic that would probably normally go through the Ceph data plane, but didn't. Although CDP kind of doesn't. It's a layer 2 protocol. So it can't be processed through Ceph because Ceph forwarding information is built on layer 3 and layer 2 information. But anyway, that is control plane protection. And then the router applies kind of standard policies to each of these sub interfaces and provides priority to the host interface, maybe a little bit less priority to the transit interface, and a little bit less priority to the Ceph exception interface. All right, routing protocol authentication. Essentially, it works the same way that NTP works. Both routers have a shared secret key, and they're sending all the routing updates in plain text, but they're sending it with a hash. Remember how we talked about how the NTP update goes through the hashing process with the key? Out comes the MAC. I send the NTP update with the MAC, and the other side verifies it based on a shared secret key. That's how all my routing protocol protection mechanisms work. No secrecy, no encryption, relies on a shared secret key. The exception to this, the exception to this is IPv6. Routing protocols for IPv6 use the native IPv6 security pieces. Well, yeah, IPsec and everything else that's built into IPv6 to do the security functions between. So we do have encryption, we do have authentication, we have all that functionality. Remember, IPsec is built into IPv6. It's part of the protocol standard. All right, here's an example where we're setting up OSPF authentication. I'm assuming you guys are running routing authentication as well. Yes, no? Should be part of a STIG. First thing you need to do is to set up a keychain. Provide the keychain a name. The name does not have to match on both sides. Provide a key ID. The key ID and the key string are very important. If the key ID for that key string is 1 on this side, it needs to match on the other side as well. We never send the key over the channel, but we do send the key ID, and that's how we identify which key we're supposed to use. All right? Now we're specifying in this particular case, we are going to go ahead and use, for our hashing process, instead of using MD5, we're going to use SHA-256. HMAC means that I have some sort of hashed MAC that I'm generating, but it includes some sort of random crypto variable. Not random crypto variable, but some unknown crypto variable. In this particular case, that crypto variable is the secret key. Then I simply apply the keychain. Well, in OSPF, you can apply the keychain on an interface, or you can apply the keychain, well, actually, let me rephrase. The keychain is always applied to the interface, but you can apply the hashing method to the OSPF process as well. That is literally everything that you need to do to set up 2 routers. You do the same thing on the other side to set up 2 routers to provide authentication between themselves. Okay, there's more stuff you can do. You can have rotating keys, so you can specify a send lifetime for a key. You can specify a receive lifetime for a key, so I can use a different key to send data as opposed to receiving data. All kinds of interesting things, but we don't need to get into all that. Here's how it essentially works. The router on the left wants to send an OSPF packet. Actually, oh, that's it, huh? There's no little fancy diagram. Did I skip over that diagram? I must have. Ah, that's the one I was looking for. You guys didn't tell me I skipped a page. All right. This is essentially, basically this is the exact same diagram we saw for NTP. The only difference is that we replaced routing update with we replaced NTP update with routing update. So we take our routing update, we take our key, we put it through our hashing process, we come up with a MAC. We send the routing update in plain text with the MAC to the other side. I take that routing update that I received, I throw it into the hashing process with the key that I have configured. I take that MAC and I compare it to the MAC I received. If they're equal, everything is copacetic. Simple. Very, very simple process. No encryption, no confidentiality, but at least some sort of authentication. What does this protect against? Man-in-the-middle attacks. It provides message integrity. It prevents somebody from intercepting that routing update and modifying values. I mean, if you think about it, if I'm smart enough, I could influence metric values to force traffic to take a different path. And then I could have some sort of device in that path that captures that data. It also prevents the insertion of rogue devices. As long as the secret key is secret, nobody can generate routing packets that you would actually be able to trust because they don't know the secret key. So at a minimum, that's what we would do it for, so that we can prevent somebody from just throwing a router in and turning on OSPF or Eigrp. So that's the configuration for OSPF. Eigrp is very, very similar. You create a keychain, you enable authentication on the interface, and you assign the keychain to the interface. So here's my keychain called Eigrp keys, key ID number 1 using this key string. Use stronger keys than this. And then I go to the interface. Interestingly enough, I never understood why this was the case. Eigrp only supports MD5, but you still have to specify to use MD5. Never got that. Maybe at some point they thought, well, maybe in a later version we'll support other types of hashing. And maybe they do now. I don't know. But up to recently, I haven't seen anything but MD5. All right. So that is the end of that chapter. We're going to go ahead and, well, let's take a look and see what we have left here. And see if we can't knock one more out. This was the chapter that I wanted to get through ideally before we ended.